Yes, Assalamualaikum warahmatullahi wabarakatuh. The name is given is Rafin of Ibrahim Aziz. Number matrix A188100. Today I will be presenting my assignment on dynamic control simulation. So this is a brief. As you can see here is the dynamic, the schematic of the distillation column. For the first question, I need to set up the mathematical modeling for each question that has been defined. So my finalized value of my mathematical modeling has been inputting inside the subsystem, which is the process. If I double click here, here as you can see is my mathematical modeling for each tray that has been defined for the SB, SD, and vice versa. So next is the volatility calculation. Here, the volatility calculation will be utilizing the Machiavelli equation. Here's the Machiavelli equation, and the known value I have obtained is here, and calculated value of the relative volatility is stated here, which is YNT equals to 0.4213. And here is the assumption that I have stated based on my mathematical modeling determination and relative volatility calculation. For the column creation in the Simulink, first we need to ensure that our mathematical modeling is defined inside the transfer function condition. And here is the workflow of my for mathematical modeling converted into the transfer function equation. And here, from here, as I shown you, here is my transfer function equation for each mathematical modeling that I have defined. Next up is the calculation on the servo control by utilizing toolbox or manual. So for the toolbox, I only use on the servo controller because it doesn't require any load or disturbance. To use the toolbox, we have to ensure that our MATLAB has already installed the simulation design control add-on. So from here, we can double click on the controller and it will prompt onto the controller configuration. And from here, we can optimize or change the value on the frequency-based response. But for now, we need to base on the transfer function because our question is based on the TF modeling. So the tuning will be here. We will clicking on this option and will prompt onto the controller tuning configuration. And here is the plot graph of our block that we have defined. And here is the tuning that we can do to achieve the desired value. But using the toolbox, it has already defined the known value, which is here. And my known value p-value is negative. So using this negative into the new, as a new tuning p-value, we can see that our block response is respond accurately to the tuning that we have determined. And here's the result of the P-controller system at negative P42. Since my value is negative, my controller will be operate in the reverse direction. So similar case for the PI controller, the procedure is also similar. Set up the value I equals 0, but using this value, my obtained plot graph is quite unstable. So I make a few changes on the I controller and obtain the accurate one, which is this one. The accurate one will be -7 instead of -7760. So I will obtain the desired plot graph, which is this one. And for the PID controller, similar case for the PI, make a few changes and I obtain the desired oscillation. For the manual, you can either use the controller box or you can use the gain block to change the PID value. So for the for the P system, I use 10, and here is the plot graph for my P control system. As for my PI, my I is 2.5, but it shows unstable condition, so I change it to 0.3. So I will obtain the very desired oscillation. And next up is the same condition for the PID with P equals to 10 and I equals to 2.5 with D equals to 1. But here we can see there's an error. So the only thing I can do is time from 1 to 10 and change PID value into P equals to 10, 0.1 and 0.1. So here is the oscillation for my PID. So here is the regulatory control, which require use of load disturbance. So here is the the final response for my result. For this one is a P control system, this one is a PI, and this one is a PI control system. For the multiple set point disturbance, here the schematic for my multiple set point. The set point will be set up on step time of 20, 40, and 60 respectively. So as you can see, the step time, as I mentioned, will be changes based on the set time I have stated 20, 40, and 60. Same goes for the PI control system and the PID, but the PI and PID control system has the same behavior of response. So for the multiple disturbance, the set point for the set point for the step time for the set point is similar as the previous one, but only difference is the load is set up on the set point of 20, 40, 60, but the load final value is 10. So from here, the P value has a little bit of changes, and the PI control system and PID has slightly changes. But as you can see, there's an effect of load differences when utilizing load on the PI and PID, where the oscillation will be a little bit higher compared to without loading. So here's the tuning as for my Ziegler. The Ziegler, as I mentioned, it must be set up on the frequency response base, as I have already shown you. And I will be using the toolbox to immediately obtain the accurate p-value, which is a negative sign, which means it will be operate reverse compared to others. And here is the SD, and this is the final result of my the overall process. And for my curve profile, the SD and the SB, I use this curve profile to determine the difference of T. So I can use this difference of T to determine the PU value for my Ziegler calculation. And using this, I can conclude that the P value I have obtained is equals to KU value. So using the P Ziegler-Nicholas formulation, I have calculated and obtained the calculated value here, and I choose the PID controller to have a better response compared to PI and PI controller, and calculated the calculated value of the PID controller I have inserted here, and here is the KU and PV value that I will be using to calculate the PID calculated KC and PID value. So here is the final result of the Ziegler-Nicholas using this PID value that I have calculated. It shows a stabilized response compared to previous one. So for the Kohon-Kun, I use the similar schematic as the Ziegler. The only difference is I disconnect the controller and connect with the setup block, so to obtain this curve profile. So I could determine the tangent and the BU and the TD value for my Kohn calculation. Here is the Kohn calculation. Since the Ziegler, I use a PID calculation. So for this case, I also use a PID formulation. And here is the calculated PID value I have calculated based on my opting value from the plot graph. And here is the finalized value of the PID overall process for using the Kohn tuning method. As you can see, CC method has a better response compared to ZN because, as you can see, the curve for the CC is immediately sharp changes, and here, compared to the Ziegler, it will gradually oscillate and like that. So although both methods give a better response, but we require other parameters to ensure that our conclusion is accurate before making a judgment. Thank you. That's all for me.